Welcome to the channel Physics Infinity. Today I'm going to take a lecture on dielectric sphere, a solid dielectric sphere. We have done a lot on the conducting spheres, and this particular one I'm talking of a uniformly charged dielectric sphere. So there is a dielectric sphere. Of course, dielectric sphere is insulating material of radius capital R, and an amount of charge capital Q is uniformly distributed well within its volume, so that it has a uniform volume charge density rho, that is Q upon 4 by 3 pi r cube. I am interested in finding what is the potential intensity at various points outside points, on the surface, and inside points, and will also be interested in calculating the total energy associated with the field of this system. The system here is that uniformly charged dielectric sphere. So let's take one by one. I take x as the distance from the center. The center is O, radius is R. So outside points, I am purposely taking outside points because for that the expressions are similar to that of the conducting charge sphere. The electric intensity, once again, if it is a uniform charge, rho is uniform, then the charge for outside points will behave like the total charge lying at the center. So it will be kq upon x square, x cap. X is the distance, inverse square fall. And the potential, just like the conducting sphere, kq by x, so no difference. I take it on the surface. On the surface, when x is equal to r, once again no difference. E is kq by r square, r cap. Same was the expression for the charge conducting sphere, and potential was kq by r. Here also it is the same. Now if a student wants to ask, well, how do you get this expression? Then of course you can apply the simple Gauss's law like you did in your 12th study of the application of Gauss's law. You can take a sphere of radius x within and the charge within that will be rho into 4 upon 3 pi x cube, and then you apply the Gauss's law, you usually get the expression for the intensity. So once again, the expressions for the intensity and potential for outside and the surface points are absolutely similar what we did in the case of conducting charge sphere. Now let's talk about inside. If you take inside x, if there is a point P inside a distance x from the center, then E will be the contribution. Now if you apply the Gauss's law, the contribution will come from the charge within 4 upon 3 pi x cube. Surely that will be a fraction of q. So just apply the Gauss's law to that, you get easily the intensity as kq upon r cube x arrow. kq upon r cube x arrow. A simple application of the Gauss's law, you can prove that. If you want the expression in terms of density, because later on if I am going to take a problem on the dielectric sphere, I might use the density. And especially if suppose this was not uniformly charged, density is a function, charge density is a function of x, then of course I will need the expression of the intensity also in terms of rho. Well, nothing to worry, because all I have to do is replace q by rho into 4 by 3 pi r cube. So in terms of density, it will be rho x arrow upon 3 epsilon naught. Both these expressions are very handy for solving our problems. Potential. Now potential in the case of conducting sphere, we had a very simple expression, kq by r, equipotential surface, equipotential volume, but not here, not here. This is not a conducting sphere, this is a dielectric sphere. So here the expression for potential, I have to use the expression of intensity as a function of x and then do the integration by the standard relationship E is equal to minus dv by dx. And with that I can get the potential at the point P, which is distance x from the center within the sphere. What do I do? Now first of all I give you the concept. The potential V will come out to be this. The potential V will be kq upon 2r 3 minus x square by r square. How do you get that? So just to help you, I give you a simple proof of that. Very easy. To find Vx inside point, I use the expression, the general relation, E is equal to minus dV by dx, the negative of the potential gradient. So dV is equal to minus E dx. I do the integration limits, x equal to infinity, from infinity to the short point. So x equal to infinity to x, infinity to x. Left side integration, it will be Vx minus V infinity. Now V infinity of course is 0, so no problem. Here it is minus E dx, x equal to infinity to x. But there is a problem. The expression for intensity outside point and inside points are not same. So I can't do a straightaway integration from x equal to 0 or x equal to x to infinity. I can't do that. I'll have to break the integration in two parts because intensity is not a continuous function. It is not a continuous function. So what I do? Very easy. I break the integration in two parts, x to r and then r to infinity. And one more thing I do, the minus sign I make plus and I reverse the limits. So it becomes x to infinity. Here they go. From infinity to x becomes x to infinity. So x to r e dx plus x equal to r to infinity e dx. Now I write the expressions for E inside. Kq by r, I pick it up from here. So pick it up from there. So kq by r cube x dx, x to infinity, x to r, and then r to infinity, I use kq by x square dx. Simple integration. This is x dx and this is dx upon x square. Limits are already there. Any student of maths can easily do this, and you solve this up, you get the answer kq by 2r 3 minus x square by r square. So Vx equal to kq by 2r 3 minus x square by r square. Same what I told you here. You have to, so I've just proved that for you to give you some help. All right. Once we have done this, let's now find the self energy. Very interesting. I have told you the energy linked with the charged body is the energy within its field, stored up within its field. Now in the case of dielectric sphere, there is electric field center to surface and also surface to infinity. So the energy I have to find in this complete field starting from x equal to 0 to x equal to infinity. But the only thing is problem again that intensity is not a continuous function. From 0 to surface it has a certain value, of course function of x, and from surface to infinity another function proportional to 1 by x square. So I'll use the same. Now what I do? I use the concept of energy density, small u half epsilon naught E square. The elemental volume, because there is a spherical distribution, I've already taught you that earlier, that the elemental, for the spherical distribution, the elemental volume dv slash will be 4 pi x square dx. 4 pi x square dx. So I'm going to do that. So the energy is u dv integral. This is volume, elemental volume, energy density, x equal to 0 to infinity. Once again, I break the integration in two parts, x 0 to r and x r to infinity, just like I did there. Now inside the sphere, the field is, so half epsilon naught k cube upon r cube x square, elemental volume 4 pi x square dx. Outside, half epsilon naught intensity k cube by x square square, half epsilon naught E square, elemental volume 4 pi x square dx. Once again a very simple integration, very simple integration. I leave that as an exercise to you. I won't do that here to waste your time and consume the time of the video. So you do this integration, you do this integration, it is q square upon 40 pi epsilon naught r plus q square upon 8 pi epsilon naught r. Now mark one thing, when I taught you conducting charge sphere, you already remember this expression, q square upon 8 pi epsilon naught r. So here it is within the outside field, but there is field inside also. So there will be energy stored inside also, and the energy stored inside is 1/5 of that, always remember. So q square upon 8 pi epsilon naught and 1/5 of that is q square upon 40 pi epsilon naught r. Add together, you get the answer 3/20 q square by pi epsilon naught r. So we've done intensity, potential and self energy. Let us do graphical study as well. So I plot the graph for intensity and x and potential and x. Intensity versus x. From 0 to r, E is proportional to x. E is proportional to x inside kq by r cube x. So on the surface, when x is equal to r, it is kq by r square, and outside, of course, kq by x square. So the graph for intensity, look at that, straight line, and then it goes like this. Potential. Now potential from this expression, when x is 0, that means at the center, it is 3 by 2 kq by r. So 3 by 2 kq by r, and on the surface it is kq by r. So the curve goes like this, and outside, of course, outside v is proportional to 1 by x outside. This is rectangular hyperbola. So it's a continuous curve. So this gives us the expressions for intensity, potential, inside, on the surface, outside, energy linked with the field, and also the graph. So this is basic study of the dielectric, electrostatics of the dielectric sphere. I can now take another video in which I can take a problem dealing with the dielectric sphere. I hope you like this video. Give a thumbs up, subscribe my channel, and I'll be happy
if you
to
love
produce
the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.